So we have two little tuning in exercises. Let's see how you went. What I expected you to do is to go 150 multiplied by pi on 180. And then I'm hoping you might be able to find some common factors of 150 and 180. Don't forget what I said to you last lesson, which is that you can always put a whole number over 1 to make it a fraction times a fraction. And once you've done a fraction times a fraction, you can use cancelling down. And if you are weak with skills like cancelling down, it is going to be difficult for you to do this fluidly or fluently, just like that. But we can see that there's a few factors here that I can go with, but let's just do it slowly. Not that slowly, but I can see that 10 goes into both of these. So there we go. We're left with 15 and 18, and then what? 3? Yeah, that'll do, won't it? I haven't had much sleep, so tell me if I get some calculations wrong. It's bound to happen. So on the top I've got 5 and pi, so that's 5 pi. And on the bottom I've got 6, so it's 5 pi on 6. All good? The other way I could have done this, did anyone do it differently?
Oh,
Hello, Jeremy.
I was having a query from kids about signing up for the maths form.
Ask Jason, I really haven't.
Right, okay.
Yeah.
There's nothing been set up for them to sign up. You're not doing anything.
No, not that I'm aware of. Not from me. Okay, so that's good to have that on the video too, isn't it? Did anyone do it differently? Remember I said to look for some of those shortcuts? Another way you could have done it, arguably it might be easier or not, is to go, well, I know that pi is 180 and I'm subtracting 30 degrees from 180 to get 150, so I could subtract pi on 6 because pi on 6 is 30 degrees. Remember how I said it's one of those common angles that you should know the radian measure of? We've done one lesson on it, so it's not like I think it should be like this for you yet, but I was just pointing it out that knowing these common angles like pi on 6 is 30 degrees, pi on 3 is 60 degrees, pi on 4 is 45 degrees, pi is 180, pi on 2, all those kinds of things, these are really useful so that you've got little shortcut ways. So pi minus pi on 6 must be 5 pi on 6, right? Because pi is like 6 pi on 6. So 6 pi on 6 minus 1 pi on 6 is 5 pi on 6. Okay, 4 pi. If you're doing it as I would have expected, it'd be a bit like that. And then cancel out the pi's. And then you'd have, what, 720 degrees? That's it. Anyone do it in a faster way, more efficient way? Or who can see it?
2 pi times 2.
Yeah, 2 pi times 2 or 2 pi plus 2 pi. So another way is to go 4 pi is just 2 lots of 2 pi. So that's just, and you do most of this in your head, right? I'm just spelling it out. 720 degrees, and that's a bit faster, I think. You'd probably do that in your head. So same with 6 pi or 12 pi, if it's a multiple of 2 pi, you can just make it a multiple of 360. So looking for those little shortcuts is a really efficient way of getting your brain to be working. What are we doing today? Today we are looking at a new rule. Last lesson we looked at the sine rule. This lesson we're going to look at the cosine rule. Okay, so in the second half of this lesson, I'm actually going to spend some time showing those who are interested how to construct the cosine rule. I generally find students who construct rules, rather than just be given them, tend to know how to use them better because they see the inner workings of the rule. So it stops being a rote learning sort of, here's a rule, apply the rule, and it starts being a, oh yeah, I get what I need. So I'll do that in the second half of the lesson. But here's the cosine rule. I might just zoom up just for the moment. So a reminder that what the sine rule allowed us to do is to work with triangles that were not just right angled. Okay, so traditionally trigonometry is built from a right angled triangle perspective. In the sine rule, we were able to apply it to any old triangle. and you can see here, just apart from the fact that I've got a wobbly hand, that's not a right angled triangle. Okay, so it's a general triangle there. And it turns out that if you've got a general triangle here, and let me just spend a moment just talking about the way I've constructed this triangle. This triangle has three sides. That's why it's a triangle. And it's also got three corners. If you didn't know that, you're in the wrong class. But importantly, I labelled the three corners A, B, C. So we technically call this triangle ABC. But importantly, the side opposite the angle is given the lowercase letter. So that's really important because sometimes you can get a little bit slack with uppercase letters and lowercase letters. Generally speaking, uppercase letters, capital letters, that's a better way of saying it. Capital letters are for vertices and angles, and lowercase letters are for lengths, like sides. So you can see that opposite vertex A is side A, opposite vertex B is side B, and opposite vertex C is side C. Can you see how that's all worked out? So it's always the opposite side is the lowercase letter. All right, Sam? Yep. Okay, so it turns out that we can generalise Pythagoras' theorem, which is c squared equals a squared plus b squared, where c is the hypotenuse. We can generalise this to this formula here, that c squared is equal to a squared plus b squared minus 2ab cos c. Now again, in the second part of this lesson, for those who are interested, I'll go through why that works, but it does work. The important thing is, I arbitrarily named these corners A, B, and C. I could have made that A and that B and that C, or that A and that's B and that C, and so on. I arbitrarily named the corners, and therefore the opposite sides would have been labelled accordingly. So even though I've got c squared equals a squared plus b squared minus 2ab cos c, I could have easily have said a squared equals b squared plus c squared minus 2bc cos a. So the important thing is that this side is on one side, so c squared. This is the square and the square of the other two sides, minus 2 times those two cos of the angle opposite that side. So you're linking this side with the angle opposite it, and these are the other two sides. That's the pattern to look at, which is why I've got 2 dot points there. And I'll show you the example so you can sort of see what I'm talking about. To find a missing side, you need 2 other sides and the angle between those sides. So look at this diagram here. I've got this side and this side given, this angle in between, and so opposite this angle is the unknown. Okay, so don't get too caught up with C's and A's and B's and whatever else. That's the shape of it in your head. It's 2 sides that you know with an angle between them, and then what you're looking for is the other side. Now maybe you're given these 2 angles, but you can always then work out the third angle. So there might be some prep work you have to do to get that information, but more or less you'll need to get to the point where you've got 2 sides, an angle in between, and then you'll be able to work out the unknown side. Okay, I'll go through that in a second so that it makes sense. Example 2, to find a missing angle, you need to know all 3 sides. That's all you need. So if I've got all 3 sides here, I can work out what theta is. Okay, moving back to, I'm going to zoom out in a second again, but I'm going to just have a look at a rearrangement of this rule. Normally I tell students don't worry about working out, don't worry about learning 2 different versions of the same rule. You can always reorganise it. But in the case of the cosine rule, I think it's worth it. It's a pretty straightforward process, so I won't go through it. You can do it for yourself if you think that would help you make it concrete. But basically, I can rearrange all of this so that cos c is on one side, and if I do that, the right-hand side looks like that. So a squared plus b squared minus c squared, so that's the 3 side lengths you need, divided by 2ab. So if you do that, that'll work out what cos c is. So then if you go inverse cos, you'll work out what C is the angle. So use that for missing angles and use that for missing sides. Okay, before I go through examples, does anyone have any questions on that? Okay, get your calculators out. Whichever one. Doesn't require a GDC. You actually can. I don't normally have one. This is going to look like the biggest maths nerd thing in the world, but I actually have one in my pocket, so there you go. Do you know how to use those ones? Hang on, I'll switch into a calculator. Okay, there you go. I'll show you how to use it as you go along. I don't have any more, but can you just share? You got a second one? Thank you. That's more maths nerdy than me, then, Ollie. You got two. Don't know how true that is? No, I don't know how true that is either, Ollie. Okay, so here we go. I'm going to go through these two examples. So with example one, I have the right conditions for two unknown sides and an angle in between. Remember, sometimes you might have to figure these things out a bit. So this is just a very straightforward application of it. And I've started by writing out the formula. You don't have to. I've just got it there for reference. So C squared equals A squared plus B squared minus 2AB cos C. My next step is then to do the substitution. So instead of C, I'm going to write X. It doesn't matter which one I choose now, but instead of A, I'm going to write 7. Instead of B, I'm going to write 10. And then I'm just going to use my little bracket notation there. So that's 2 times 7 times 10 multiplied by the cosine of 60 degrees. Okay, so that's a straight substitution. Now what I do from here is I just use my calculator. So I'm going to give you a moment to get ahead of me. I just want you to work out this next step.
Yeah. Well, I haven't seen the rule.
Oh, cool.
Yeah.
But Trig's okay though. So there's a square button there, and then you get cosine. Everything's okay. Yeah, and you get cosine. Yeah, Is that calculator okay? You following okay? Okay. Just as a practice of using the GDC, I'll quickly fire up my GDC, my Goodaka. I say quickly fire up. I just realised that because I'm recording the tab and not the window, this will not be on the video. So that's a bit of fun for us all. So I'll pause the video and then I'll just show you the calculator work. Okay, so once you've used your calculator, you get 79 is what x squared is. I often find that students sometimes forget to then square root the result from here. Remember, this is what x squared is equal to. So therefore, x is equal to the square root of that, which is 8.89, which is what we worked out on our calculator. And maybe units at this point would be good as well. So if you've got 8.89, very well done. How about I give you a chance to do a similar sort of thing for example 2? Get ahead of me, see how far you can get. I'll give you a minute's head start and then I'll go through and do it myself. Okay, let's see if you are able to do similar to me. So the C in this case is theta, so I go cos theta, is equal to, and again, it doesn't really matter what I do as long as this C and this C are matched in the diagram. So 6 and 3 doesn't matter, but the 5 does. So it's going to be 6 squared plus 3 squared minus 5 squared all over 2 times by 6 times by 3. And we can use our calculator to do that. I'll just pause the video and go over to the GDC to do that. Okay, so, oh man, what was it? So when I work out that right-hand side, I get, I think 0.5 recurring. The calculator says 0.555556, but I'm pretty sure it's 0.5 recurring. And so theta is, I mean, I wouldn't do this step normally, but I'll just do it for the notes, is cos inverse of 0.5 recurring. And that is equal to 56.25 degrees. And that's basically it. You could convert that into minutes and seconds, but I'm pretty sure in Maths Methods Foundation, you don't have to work out minutes and seconds. So there you go. Anyone got any questions? Want to do some practice? All right. So I'll stop the video here.